Hello, everyone. So today we're going to be talking about ocean acidification, which is known as global warming's evil twin because they go hand in hand. So before we can get into any of this, we need to know about fossil fuels. Fossil fuels are how we as Americans get most of our energy, about 63%. This is actually down from over 80%. We've been very dependent on fossil fuels as our energy source for many, many years. So, fossil fuels produce energy because when you burn them, fossil fuels are hydrocarbons. They're made up of decomposed organic matter. When you burn them, they react with oxygen. It releases a lot of energy. It's an exothermic reaction. And we've seen this combustion reaction before, right? We have our hydrocarbon here, our fossil fuels such as coal or natural gas. It reacts with the oxygen in the air. It produces carbon dioxide and water, but most importantly for our purposes, it produces energy, right? It's really hot when we're by a fire, when we use fire to cook. This is this sort of combustion reaction here, and it produces a lot of energy that we can use and take advantage of. However, one of the important byproducts of this is all the carbon dioxide that's also being produced, and that has ramifications that we'll be talking about. So, this is a general outline of how a coal-fired power plant works. So we have our coal, right, or our fossil fuel. We burn it in a controlled environment, and all that heat from the combustion heats up water that we run through these pipes here, and then it evaporates it. It turns into steam. That steam is funneled and moves these turbines, which in turn produce electricity for us to use. So we're essentially boiling water and using that steam and that heat in order to produce electricity that we use every day. However, that combustion, it produces a lot of steam. So if you see power plants in real life, a lot of the time you'll see steam coming out of these pipes. It's really big and white, looks like clouds, because it essentially is clouds. But a lot of carbon dioxide is also being emitted in this process because when you burn a hydrocarbon, you emit carbon dioxide. So there's a natural cycle to carbon dioxide. Carbon dioxide is an important part of our ecosystem. Plants, right? Plants use carbon dioxide for photosynthesis. They take some energy in from the sun. They use carbon dioxide and water and synthesize some sugar out of it, some glucose that they use for their energy. We in turn eat glucose in our plants and stuff like that. And so there's a nice cycle that naturally occurs between carbon dioxide and oxygen. And then animals, once they die or are waste, right, it goes back into the environment, turns into fossil fuels, which we then are burning and using as fuel. Here's a slightly more in-depth image. You'll see that it's not just animals breathing and plants using that carbon dioxide, right? Carbon dioxide comes from combustion in our day-to-day lives. It comes from us using fossil fuels in our cars and these power plants. When there's big events like volcano eruptions, right? Those use a ton or produce a lot of carbon dioxide. That carbon dioxide, a lot of it's being used by plants, but most of it's just going into our atmosphere, right? About 70% goes into our atmosphere. However, about 30% of it is actually absorbed by our large bodies of water, notably the ocean, right? So the ocean isn't just pure H2O molecules floating around. There's lots of dissolved salts, animals. There's also gases dissolved in there, which is why fish and animals with gills can breathe the oxygen through. They can take out the oxygen from the water. It's not actually taking out oxygens from the individual water molecules. It's instead harvesting the dissolved gas in the water, which is why you need a bubbler in your fish tank if you have one. So you'll see that there's a very complex system here. But the thing is, when we are producing a lot more carbon dioxide than's naturally occurring, that system gets thrown out of balance. So this is called the Keeling curve. It's developed by a scientist with the last name of Keeling, and it's measured the atmospheric CO2, so the carbon dioxide in our atmosphere, from a long time ago up until recently, and it's still measuring, still going as we progress, right? So our x-axis is time or years, our y-axis is atmospheric carbon dioxide, and we're measuring it in what we call ppm, which is parts per million, meaning that for every million air molecules, if it were right here, there'd be 340 of those air molecules would be carbon dioxide. So you'll notice that the actual readings, the day-to-day readings, aren't a straight line, right? We have this sort of, looks like a sine graph almost, this sort of up and down pattern to it. And this happens every year. And the reason for that, right, is that we're all constantly producing a lot of carbon dioxide, animals and us burning things. That's happening year round. But the plants that are using up that carbon dioxide, we get a lot more of them in the spring and in the summer, right? That's when plants are most alive and are photosynthesizing and using up carbon dioxide the most. So starting around April or so, that's when plants are really starting to use up that carbon dioxide. So the carbon dioxide concentration goes down until we get to fall, right? That's when most plants go dormant or die. And then it starts to increase again. So we have this yearly sort of cycle of carbon dioxide that's pretty small on the grand scale of things, but it is notable. And you'll see that happens every year. However, what's important is that the overall trend, right? If you just draw a nice linear line going through sort of the average throughout the year, that's going up, and that's going up really, really quickly. And that means that the overall carbon dioxide content in our atmosphere is increasing notably, right? It's much higher now. We're way past 2005 at this point, but in 2005 than it was in the 60s or the 70s or the 80s, right? It's increasing. So why is this important? So what? So increased carbon dioxide concentration has two main effects, right? Two main environmental effects. One, global warming. So carbon dioxide is what we call a greenhouse gas. And what that means is that essentially it traps in the energy from the sun from bouncing off the earth and back into space, meaning that overall that heat is trapped on our planet and the overall temperature increases slightly. About 70% of our CO2 gets stuck in the atmosphere. That's what's used on the plants and stuff like that. But another major one is ocean acidification, and that's what we're going to be talking about today. Because again, about 30% of that carbon dioxide that we're emitting isn't just floating around in the air, it's instead going into the ocean, being dissolved into our water. So when scientists first figured this out, they thought, oh, that's great, right? The ocean is acting as what we call a carbon sink, meaning that it's absorbing that water or that carbon dioxide from the air, meaning we don't have to deal with repercussions, right? It's all just going into the ocean, so we don't have to worry about it. However, there are issues that go along with that. So before we get into the issues, let's talk about the actual chemistry that's happening. So the water in the ocean reacts with carbon dioxide. So at the beginning of this unit, we talked about how water and a non-metal oxide, right? Carbon is a non-metal. So water and a non-metal oxide create an acid. So if we have water here plus carbon dioxide, these react and make what we call carbonic acid. So in the ocean, the more carbon dioxide we're dissolving, because there's plenty of water in there, but the more carbon dioxide we dissolve, the more carbonic acid is being produced. And carbonic acid is an acid, so it doesn't just stay in this molecule, it dissociates or breaks apart into H plus and what we call the bicarbonate ion, which looks like this. So it releases these acidic hydrogens, that's what makes it an acid, and produces this bicarbonate ion here. So now we have a lot more of these bicarbonate ions floating around, and we have these H pluses or acidic protons floating around as well. And so these H pluses don't just sit around on their own. Instead, naturally, there's a lot of carbonate ion in the ocean already, CO3 2-. That's important for a lot of the animals that live there. But the hydrogen here will attach to it and create more bicarbonate ion. So we have a lot of bicarbonate, one from the carbonic acids being produced here, and two, the other hydrogen that breaks off is taking up some of the carbonate that's already in the ocean and making even more bicarbonate. So we're producing bicarbonate two ways. One, from the carbon dioxide, and two, from the extra acidic hydrogen taking up some of the carbonate that's already there. And so this is important because it affects our wildlife. So here, again, you'll see another graph. As atmospheric CO2 increases, right, as we get more and more carbon dioxide on the Keeling curve like we saw before, the amount of carbon dioxide in the water, dissolved in the water, also increases. That's what this dark blue is here. And as that happens, from that first reaction that we saw on the previous slide, the pH, or the acidity of the water, goes down. So we're decreasing the pH of our oceans by increasing the carbon dioxide content both in our atmosphere and in the water. You'll notice that our ocean pH is between 8.1 and 8.2. It's somewhere in this range. So ocean water is actually basic because of the salts that are in there. However, life has adapted to that certain pH. So even if we're decreasing it just a little bit, while it's still not actually acidic, it's more acidic than it was before, and that can cause some problems. Most notably, it affects our sea life, right? So seashells on big crabs, crustaceans, stuff like that, as well as a really small zooplankton in the ocean, are made up of calcium carbonate, so CaCO3, which is an insoluble substance. That makes sense, right? They're in water. They don't want their shells to dissolve. It's nice and solid and works well for them. They're able to get calcium and carbonate from the water around them, from their diet, and they can create these shells naturally. However, as more of that carbonate that they get from the water is turned into bicarbonate, there isn't enough actual carbonate for all the animals that need it, right? So if you need this stuff from the water around you in order to make your shells to protect yourself, and you can't because all of a sudden there's not enough of the elements or the ions that you need, you're going to have some problems. Instead, naturally, they start making calcium bicarbonate instead, right? They don't have carbonate, but they can use some of this. However, that's a much, much weaker substance. It's somewhat soluble in water, so it's like if you scratch it or pick at it, it'll start to dissolve some, and that doesn't make for good protection from the environment and from predators around you. So here we have another nice visual of what we've been talking about, right? As we put more atmospheric carbon dioxide into the atmosphere from burning a lot of fossil fuels, it naturally dissolves into the water. Again, about 30% of it dissolves into that water. When that happens, it creates carbonic acid, which in turn creates bicarbonate and acidic hydrogens, which affect the pH. So the carbon dioxide makes carbonic acid, and then that bicarbonate reduces the amount of actual carbonate that organisms have in order to make their shells. So this has long-standing effects, right? It depletes the oceans of the compounds that they need to make their skeletons. Fish have problems because they have a differing pH than what they're used to. And then if you're killing the stuff at the bottom of the food chain, right, all this zooplankton and these little clams and coral and stuff like that, it affects the whole rest of the food chain. If you think about your ecosystem discussions from bio last year, you'll know that if you take away the bottom pillar of your food chain, right, then everyone on top, everyone who benefits from eating those smaller animals, also is negatively affected. So again, like I mentioned earlier, oceans aren't actually acidic, right? Ocean acidification is a real thing. That doesn't mean that oceans are going to, irritate your skin because of how low the pH is. That's not what's happening. What's happening is that the average sea level pH of about 8.16, that's going down, right? And that's dangerous in of itself. So even though it's a relatively small change in the pH that we're seeing right now, just from like 8.16 to about 8.13, 8.10, something in that sort of scale, things are still being negatively affected, right? So again, the pH scale is a logarithmic scale. So if we went from 8 to 7, that's a tenfold, 10 times as acidic as it was before. So just changing by this small value is actually about a 30% increase in how acidic the ocean is right now, and things are just scaling up, right? If we don't stop using as many fossil fuels or find a solution to this problem in the future, or a cleaner alternative energy, then this problem's just going to keep ramping up and become even more and more noticeable. So again, here's a nice image, and it has a timeline at the top too. So you'll see before the pH was approximately 8.2, and then right now it's at about 8.1, right? Which again, that doesn't seem like a big change. It seems like, oh, that's pretty negligible. However, this is over a huge body of water. And as this is happening, right, all of our coral, all of our lower level sort of life that depends on the carbonate ion is being negatively affected here. The thing is, if you project based on our usage and we don't change anything, give it another, 50, 60 years, we'll still be alive to see the pH drop even more drastically. And at that point, a lot of species are going to die off. We're going to have a lot of huge issues, not only for our ecosystems, but for us personally, because we use a lot of food and resources from the ocean. And if these resources are robbed of us, we're going to have some problems as humans. So again, here's some graphs showing what would actually be going on. So today, all these are related, right? Our pH is just over 8. As our carbon dioxide, right, if we use more and more of it, our pH would decrease, meaning that we would have less and less of our carbonate ion, which is what's important here. This is what the animals need in order to make their shells. So as we move our pH further to the left, our carbonate ion would decrease even more drastically, causing a lot of potential issues in the future. And there's tons of life in our ocean, right? There's lots of beautiful reefs and animals and species that we haven't even necessarily discovered yet. It seems like every couple of weeks I see some article about a new fish or something that they saw for the very first time. And we've been exploring our oceans for as long as humanity's been around. But you can see, and hopefully you'll be able to watch a documentary I'll talk about later on called Chasing Coral, which is great. You can see that these coral reefs, which are beautiful, are dying, right? Because of one, global warming from all the carbon dioxide we have, and two, this issue of not being able to create the calcium carbonate skeletons that they need. There's lots of ramifications of this, right? You can see on a microscopic level, here on the left, we have some coral that was able to build its skeleton properly, whereas on the right, you'll see one that had a more acidic environment. It was not able to build the calcium carbonate that it needed to, and it was not nearly as strong. So there's a lot going on here, and I hope that we're able to keep this in mind when we turn on the lights, and hopefully we'll be able to come to a cleaner energy resolution as a whole, as a race soon.